So the next step in hypothesis testing is setting up what we call a rejection region here. So that's where the sample statistic, the test statistic, is too extreme to be due to chance. So let's go back to our example 1 on the action level for lead there. So let's go ahead and state our null and alternative hypotheses. So start with the alternative. That's what you're trying to show. So we want to know, the question is there enough evidence to conclude that the mean for all schools in the district is over the action level, which was 15 parts per billion? So that would be mu greater than 15. And then our null, if that's not the case, we conclude mu equals 15. Population mean is 15, not over the action level. So to decide whether or not to reject this null hypothesis, we're going to measure that by forming a test statistic. So the test statistic is really the z-score of the sample data. So you've got your sample statistic. That's the information you get from drawing your sample. And what you do is you compute the z-score of that sample statistic. So the mean for your sample minus the mean that you're hypothesized, for us that's the 15, and then divide by the standard deviation of the X-bar distribution, the sampling distribution. That's where sampling distributions come into hypothesis testing, because that X-bar comes from the X-bar distribution. We want to know how extreme is it in relation to that distribution. So that's X-bar minus mu 0 over sigma divided by root n. So that's the number of standard deviations X-bar is from that hypothesized mean. So that rejection region in relation to our hypothesis test can take on one of three forms. It can be lower-tailed, upper-tailed, or two-tailed, depending on what your alternative hypothesis looks like. So our numerical values for the test statistic, for which we're going to reject the null hypothesis. That is, if z's in the rejection region, we reject the null hypothesis and accept the alternative. That's what the rejection region is. It's the values for which you reject H0. So the rejection region is chosen so that alpha, the significance level, is a probability of a type 1 error, which is the area of the rejection region. So the value of alpha we usually choose to be small, like 0.01, 0.05, or at most 0.10, and that's called the level of significance of the test. So here's a picture. Alpha is our significance level, which is probability of type 1 error or area of the rejection region. So mu 0 is our hypothesized mean. So if we have a lower-tailed test, then our alternative is that the mean is less than the hypothesized value. The null is that it equals. So you've got your hypothesized value here in the middle. So that is a mean of mu 0, and that's got a z-score of 0. And then if it's a lower-tailed test, your rejection region is going to be on the left. So if your test statistic, the z-score of your sample data falls over here, you reject H0. And then we want to know what's the cutoff there. Well, this area here is alpha. So that means that this is going to be the negative of Z alpha if you're looking at a lower tail test. And so given, depending on what alpha is, that's going to determine what that value is. So for example, if alpha is 0.05 and you're doing a lower tail test, then that z-score is going to be negative 1.645. Now if you're doing an upper tail test, you've got your mu 0 in the middle. It's got a z-score of 0. And then your rejection region, since mean greater than, we're trying to show the mean is greater than mu 0, our rejection region will be on the right. So if the z-score of our data falls over here, we decide that it's too extreme to be due to chance, and we reject H0. And the area of that little tail there is alpha, so this is going to be Z alpha. Remember Z alpha, right area alpha. And then this is the negative of that number. So for upper tailed tests, these are the most common values of alpha, and then these are the common cutoffs for that rejection region. And then if you got a two-tailed test, so that comes from an alternative hypothesis that's showing a difference, not directional, then your mu0 again in the middle corresponds to a z-score of 0. And then you're going to have two rejection regions, one on the right and one on the left. So if your test statistic is extreme large or extreme small, then you reject H0. So reject H0 there and reject H0 here. Now each side here, the alpha is the area of the rejection region here and here. So total alpha, so that means alpha over 2 on each side. So this value is Z alpha over 2. And then this is the negative of Z alpha over 2. And then for the common values of alpha, those are these cutoffs. For 10%, plus or minus 1.645. For 5%, plus or minus 1.96. And for 1%, plus or minus 2.575. So the next step that we haven't done is figure out where, what is our value of our test statistic? What's the z-score of the sample data? So if it falls over here, we reject the null. If it falls over here, we don't. In an upper tailed, if the test statistic falls over here, we reject the null. If it falls over here, we don't. And for two-tailed, if it falls in either tail, we reject the null. If it's in the middle, called the non-rejection region, we do not reject. So let's go back to example 1 again. So our null was mu equal 15. Our alternative is greater. This is an upper tailed test. Our alpha is 0.05. So 0.05, upper tailed 1.645 is the cutoff for the rejection region. So to the right of 1.645, we will reject the null hypothesis. So we compute the z-score of our sample data, and if it's bigger than 1.645, we decide that this can't be due to chance. There has to be an actual effect here. So, and then this area right here is 0.05. So that's setting up the rejection region.